It is Monday. It's a Monday. Morbid Monday. Oh my word. Let me pause the recording. Am I still recording? It is a little sad. I'm sorry. I should have been a little bit more prepared for that. But it's okay. I'm sure we'll do something fun tomorrow. So, on Friday, we started lecture 3.3. What was lecture 3.3 about? Acid what? Rain. Acid rain? I mean, sort of, I guess. I think that was what we talked about on Thursday. Jacob.
We talked about different types of acids and bases.
That's right. Different types of acids and bases. And what were some of those types of acids and bases that we talked about? Owen?
What was Arrhenius?
Arrhenius. And what is an Arrhenius acid or base?
The acid is when it increases hydrogen ion concentration when dissolved in water, and the base when it increases hydroxide ion concentration when dissolved in water.
Very good. It's specific to the hydroxide, which is H3O plus, or sometimes just H plus. That's fine too. If an acid is dissolved in water, or if it's dissolved in water and it increases the hydronium ion concentration, that is an Arrhenius acid. Colin?
Bronsted-Lowry.
Bronsted-Lowry. And what is a Bronsted-Lowry acid or base?
The acids donate the hydrogen ion, and the bases accept.
Very good. An acid will donate a hydrogen ion or a proton, and a base will accept that. Very good. And what was the last one? Yushin?
Lewis acid.
Lewis acid and base. And what is a Lewis acid or base, Abigail?
The acid.
That's fine.
The acids are electron pair acceptors, and the bases are donors.
Very good. We're talking about, for Lewis acids and bases, not hydrogen ions anymore. We're instead talking about electron acceptors and electron donors. What are the other words that we use for electron? Yeah, Zach?
Acceptors, electrophile, for donators, nucleophile.
Very good. An electron pair donator is a nucleophile, and an electron pair acceptor is an electrophile. Okay, if it accepts electrons, it wants electrons. Electron phile, love. Electrophile, it wants to have those electrons. Okay, that's how I remember it. It's a kind of a roundabout way, but I remember things weirdly sometimes. And then we talked about KW. What's KW? We did talk about that, right?
Yeah.
Okay. Sorry. I was like, I couldn't quite remember where we ended. I think I have an idea though. Zach?
Equilibrium constant of water.
The equilibrium constant of water, correct. And what is the reaction for water? Like, what is that reaction that is being described by KW? Yeah?
H3O plus hydrogen negative.
Okay, yes, very good. It's the, there's a special word for it. Does anybody remember what that reaction's called, Abigail? That's right. The autoionization of water. It's the reaction that happens when two water molecules react with each other to form one hydroxide and one hydronium. Okay? And that is true for all water things. Whenever water's a thing, it's in that equilibrium. All right, so that is true there. And then we went from there, we talked about pH. What does the P mean in front of the H? Shadia?
Negative log base 10.
Negative log base 10, that's right. And so I'm going to make sure that this is not going to try to take off in space. There we go. All right, so let's pick up where we left off. We kind of literally went straight from pH, and then I said, well, I have example problems, but we don't really have time to do them. So here's the example problem that I wanted to go over first. Just what's the pH of a solution, where, and I'm going to give you a bunch of hydrogen ion concentrations. What is the pH of a solution where the first one, the hydrogen ion concentration, is 1.0 times 10 to the negative 7. And the second one, the hydrogen ion concentration, is 1.0. Whoops. times 10 to the negative 12. In the third one, the hydrogen ion concentration is 1.0 times 10 to the negative 1. In the fourth one, the hydrogen ion concentration is 1.0. In the fifth one, the hydrogen ion concentration is 2.0 times 10 to the negative 7. And in the last one, the hydrogen ion concentration is 5.23 times 10 to the negative 4. What are the pHs of each of these solutions? Also, I don't know if I mentioned this already, but pH, when you're calculating it, it typically goes to 2 decimal places regardless of the number that is in the argument for the logarithm, okay? So however many sig figs your concentration has, you usually go to 2 decimal places for your pH, okay? Yeah, I think I mentioned that on Friday, but yeah. So who has the first one? You're gonna say it out loud. 7.00, right? And other units for pH? That would be a no. There are no units for pH. Once you take the logarithm of the number, the units are like, see ya. What's the pH of the second one? 12.00. Okay, let's make sure we're saying those decimals. What about the third one? No. The pH of the third one should be positive 1.00. Okay. What about the pH of the fourth one? 0.00. Very good. What about the fifth one? 6.69. 6.70. Thank you. And the last one? 3.2. 8. Okay, cool. So these are the pHs of these specific solutions with these individual hydrogen ion concentrations. This should be relatively straightforward. Yeah?
Why is it 2 places past the decimal point?
So that would get into like how to calculate or how to do sig figs for logarithms. Basically, the number of sig figs in your, like we have log base 10 of a number. The number of sig figs in your argument, what's in the parentheses, is the number of decimal places you go to for your evaluated answer. Okay, so generally speaking, this is not common knowledge at this point in time. I didn't learn this until I was a junior in college. And so, like, just go to 2 decimal places. They're not going to dock you points if you go to 2 decimal places when you're talking about a pH value. So, good question. Is there
not 2 sig figs in an argument?
There's 2 sig figs in the argument. So then you go to 2 decimal places in your answer.
Is that 3 sig figs?
It's 3 sig figs, yeah. But this is actually, the number of sig figs in your argument is the number of decimal places in your answer.
Okay.
Yeah. Maddie?
So for the last one, would you do another decimal?
Oh, yes, yes. Technically, yes. But we're just going to go to 2. We're just going to go to 2. Good catch. Good questions. Any other questions? Vincent?
Will we be expected to know this?
No. Yeah. I didn't have it in my notes, but Jacob asked, and so then I said. So basically all you're doing is you're taking the hydrogen ion concentration and you're taking the log base 10 of it, okay? Negative log base 10, okay? So immediately we can kind of see some patterns here. If you're not familiar with how logarithms work, you should be able to notice some of these patterns here. if it's 1.0 times 10 to the negative something, okay, or just times 10 to the something, the pH is going to be the negative of that power, okay, because it's log base 10. And so when you, again, I don't want to get too much into it, but basically if it's 1.0 times 10 to the negative 7, the pH is going to be 7. If it's 1.0 times 10 to the positive 2, the pH is going to be negative 2, okay? And so we can kind of estimate what the pH is going to be from the hydrogen ion concentration values just by kind of understanding that relationship there, okay? AP will want you to be able to understand, like, oh, the pH here is going to be in between 6 and 7. We'll want you to be able to do that on a multiple choice question because you don't have a calculator on multiple choice, okay? So practice with this, see if you can figure out the patterns, and you should be good. Now let's organize these in order of increasing pH. Which one is the most acidic here? Alex? 0. That's right. The lowest, the lower the pH, the more acidic it is. What's the next one? 1. Very good. The one after that? 3.28. What about number 4? Number 5, 7, and then this one is the last one. This one is the most basic, you would say. Now let's just kind of flip the script on this. This is kind of the same example. What is, we're just going to kind of split this down the middle. What is the hydrogen ion concentration of a solution where, we're not going to do as many of these, but where the pH equals 3.10, negative 1.34, 10.67, and 14. Okay. The hydrogen ion concentrations of each of these. Do we know how to do the inverse of a log? How do we do an inverse of a log? Kishan?
10 to the.
That's right. 10 to the power of whatever, right? Now, if we're going to do the inverse of this, if we know that pH is equal to negative log base 10 of the hydrogen ion concentration, how do we undo this? How do we solve for the hydrogen ion concentration? Owen?
10 to the negative whatever the pH is.
Good. 10 to the negative pH will be equal to the hydrogen ion concentration. Okay? Make sure you're doing 10 to the negative pH, otherwise it's going to be a massive number. Okay? So that's how you would calculate these. So go ahead and do that. Who has the hydrogen ion concentration for that first solution? 7.9 times 10 to the negative 4. Very good. What about that second one? 400. Really? Yeah, the pH is negative here. Should be a number bigger than 1. Mm-hmm. 22. Third one? Maddie?
2.1 times 10 to the negative 11.
Good. 2.1 times 10 to the negative 11. And the last one? if it's a whole number, it's also kind of becomes pretty easy. It's just 1.0 times 10 to the negative 14. Okay. So round pHs are pretty nice, and 1.0 times 10 to the something power are also pretty nice. Yeah, Maddie.
So you said for the first example that they might give you the concentration and then kind of multiple choice and say this is about like how much.
Yeah, they would say, what is the pH of
Would
this?
they do it for these ones too?
They absolutely could, yeah. So be comfortable, basically, with the conversions between pH and hydrogen ion concentration. They might say, oh, the pH of this solution is 3. Like, how many moles of this are reacting? And you would be able to,
Without a calculator.
Without a calculator, yep. So just be comfortable with the conversions there, the log base 10 and the 10 to the negative pH. Jacob?
What is a negative pH?
A negative pH is just a really acidic solution. They do exist. It's usually in concentrated strong acids or specific kind of scary solutions that we don't usually deal with in a chemistry lab. But yes, negative pHs are allowed.
It would be a great segue into a morbid Monday.
It would be a great segue into a morbid Monday. I don't have one for you though. I wonder if there's one about a piranha solution. Have you guys heard of piranha solution? Hot sulfuric acid and like hot concentrated sulfuric acid and concentrated hydrogen peroxide will like almost instantly dissolve anything organic. And so if there's like glassware that's really, really difficult to clean, like some labs, it's a last resort, but some labs will make piranha solution to clean out the glassware. Because it literally just destroys everything that it touches, except for glass, obviously. But yeah. Fun stuff. What are the units, by the way, for these? It's concentration, so it should be moles times decimeters to the negative third. Okay. Very good. Any questions on this? We don't understand this. The rest of this unit is going to be horrible. Yeah, if you don't know how to find pH from hydrogen ion concentration or hydrogen ion concentration from pH, you're going to have a rough time. Do we understand this? Okay. Yes, Vincent.
So if they give you a pH of 14 without decimal places after it, then wouldn't it be 0 sig figs if you went back?
No, because the sig figs for how you calculate this are a little bit different.
Okay.
So just again, they're not going to dock you points on sig figs for calculating pH, and I doubt they'll dock you points for calculating sig figs for that too. I usually go to either 1 decimal place for this or 2 decimal places, and it's arbitrary. I don't have a rule for how I do that, and I don't think there really is one that matters. Colin? It absolutely is. Yep. You can have things more basic than a pH of 14. Good question. Yeah, Tiny?
So for questions, I think in the mark scheme, the sig figs would just be like they give you the range, like 2 to 4.
Yeah, so sometimes on mark schemes they say your answer is, it has 2 to 4 sig figs.
Okay.
And that's fine. Okay. Usually if your answer has 1 sig fig, that's not good. So try to go 2 to 4 for ACE. Jessica?
What's something with the pH of
Above 14? I don't have an example of a more basic than 14 thing off the top of my head, but I'll get back to you on that one. Because pHs, that range outside of that are interesting to me because usually you're taught like, oh, it's only, between these things, which isn't true. But again, teaching is mostly lying, so there's that. All right, so now this should be pretty impressive because if they give you a problem and they just say, oh, and the pH, by the way, of the solution is this, you actually have the equilibrium concentration of the hydrogen ions. Okay? And so this immediately becomes something that can be applied into our unit that is equilibrium, and it allows us to set up some pretty unique situations as far as those calculations go. And so we have 2 instances where we will have these calculations show up. The first one and this is section 2. The first one is the pH of a strong acid. Okay? Or, pH of a solution with a strong acid or base. So pH of a strong acid / base. Okay? Now, what's the definition of a strong acid? This is important for these types of questions. Jessica? An acid that completely dissociates in water. Okay? Such acids are never liquids. So if you're writing out the solids, the states, the state symbols for a specific strong acid, you will never write liquid for a strong acid because it doesn't exist. There is no such thing as sulfuric acid liquid. It's actually sulfuric acid aqueous. Okay, because the aqueous solution defines it to be completely split into its ions. Yeah?
Do you have like solid?
Solid sulfuric acid? Not that I'm aware of. Because it completely, you can't have 100% sulfuric acid either. Jessica? Weak acids absolutely can be liquids because it actually exists, right? Because it exists in equilibrium. Yeah, they can be aqueous and liquids. Very good question. And so here, let's take hydrochloric acid for an example, HCl. This completely dissociates. This is not an equilibrium reaction. This completely dissociates into hydrogen ions and chloride ions. Okay? So completely dissociates in there. You could also write this as reacting with water and then just have hydronium on the product side. That's the same thing. Okay? But basically, if you have a strong acid or base question and they give you the pH, that's a pretty easy question. This is not an equilibrium problem, okay, because it's a strong acid. All right, it's not equilibrium because it's strong, and so basically the concentration of HCl, so because it's a strong acid, or we'll say base, because strong base is also completely hydrolyzed, all right, break apart. Because of this, the concentration of HCl equals the concentration of H+. Okay? And so usually we'll say, oh, the concentration of this hydrochloric acid solution is 2.0 molar. That also means that the concentration of the hydrogen ions is 2.0 molar, and the concentration of chloride ions is 2.0 molar. But we usually don't care about the chloride ion concentration. For acids, it's hydrogen ion concentration. Okay? And so since there's no reverse reaction, this is true, and it makes it pretty straightforward. Okay? The same is true for bases. Here's a strong base, sodium hydroxide. Now we do have solid sodium hydroxide, and so we could say sodium hydroxide, solid, plus H2O, liquid, okay, will give us a reaction that is aqueous sodium plus sodium plus, and then aqueous hydroxide. Now, if I was actually being super picky here, this would not be H2O liquid, this would be aqueous. Okay. So this right here is a pretty standard reaction for dissolving something, making it an aqueous solution. Okay. So again, here, this is not an equilibrium reaction, so the concentration of our NaOH solution is the same as our concentration of our hydroxide. Okay. Okay. This is important to realize before you attempt to basically set up an ice table and then realize, oh wait, I didn't even have to do that because it's a strong acid or strong base. Okay. So that's it. I don't have anything else to say here. Jake?
How do you actually determine if something's a base?
How do you determine if something's a base? Well, we have 3 definitions for how you can make a base, right? What's the first one? Arrhenius? What's an Arrhenius base? Zach? It increases the concentration of OH. What's the Bronsted-Lowry acid or base definition? Zach?
Acceptor of H plus.
An acceptor of a hydrogen ion. And then the Lewis base definition? Alex?
Donates an electron pair.
Donates an electron pair.
Does not have hydrogen.
This has hydrogen. Okay?
Hydrogen.
Let's try not to make rules that are overgeneralized and then might hurt us later. Okay?
Like that's hydroxide.
Right. But it has a hydrogen. Okay?
And then like it's not.
And, okay. I'm not gonna argue this. If you want to make rules like that, you can. Just be careful. Okay? Because it may not be true in every single
They
scenario.
all have OH.
Nope.
Okay.
Nope. Not every base will have OH. Ammonia is a base. Ammonia does not have an OH group. All right, number 3. This is where things really get spicy with weak acid-base calculations. Okay. So since weak acids and bases are in equilibrium with their ionization self, we actually have a specific K value that is associated with weak acids and weak bases. Okay? So since they're in equilibrium, since weak ABs are in equilibrium, we have a K value for acids. So for acids, we have a Ka value. Okay? The equilibrium constant for an acid dissociating. We call this the acid dissociation constant. Okay? It's basically just a specific K value for an acid. All right? So we calculate it the same way we would calculate any K. It's just specific to an acid dissociating in water. Okay? So if we have acetic acid, which is CH3COOH, acetic acid, okay, as a liquid, plus H2O as a liquid, is going to be in equilibrium with H3O plus aqueous, plus acetate, which is CH3COO minus, also aqueous. Okay? This is the equilibrium reaction for the weak acid acetate. Okay? Or acetic acid. Now, here, I should do this instead. This is COH. We'll say this is aqueous, just because it's dissociating. Okay? Now, this right here, okay, we can write the Ka expression for this. Remember, we don't include water as a liquid if there's aqueous things. Okay? So here we have aqueous, here we have aqueous, and here we have aqueous, and here we have liquid water. We're not going to include water in our K expression here. All right? And so this is going to be H3O plus times the concentration of acetate divided by the concentration of acetic acid. Okay? This is the Ka expression. Okay? Note that you can actually, there's values called the pKa, which you would expect to be just the negative log, base 10 of the Ka. Okay? pKa values typically represent how strong an acid, a weak acid is. Basically, how much toward the products or how much toward the reactants that equilibrium is. The lower the pKa, the stronger the acid. Okay. So, oh, and then generally speaking, the Ka can be calculated from this generalized acid dissociation reaction where we have Ha, aqueous, okay, in equilibrium with H plus aqueous plus A minus, which is the conjugate base of our HA acid. And so our generalized formula for Ka becomes Ka equals the hydrogen ion concentration times the conjugate base concentration divided by the acid concentration. And these are all at equilibrium, okay? Because these are K values we're talking about at equilibrium, not initial values, at equilibrium, okay? For bases, it's pretty much the same thing, okay? But instead of a Ka, it's, of course, a Kb. So for bases, for weak bases, we have, you know, ammonia as a base, like I mentioned before, so NH3 aqueous plus H2O liquid is in equilibrium with ammonium, NH4 plus aqueous, and OH minus aqueous. Okay? And so the Kb for this reaction is, you know, just the same thing. We exclude water because everything else is aqueous. The Kb for this is the concentration of ammonium times the concentration of OH minus divided by the concentration of ammonia. Okay? Again, generally speaking, our generalized formula or equation for Kb would just be our base, aqueous, typically, okay, plus water gives us Hb plus, which is our conjugate acid, plus OH minus. Okay, this is also Kb. So our Kb expression comes out to be the concentration of Hb plus times the concentration of hydroxide divided by the concentration of our base. Okay, I'm going through this kind of quickly because it's just talking about how to calculate K. Maddie.
When you wrote the generalized equation for that,
Yeah.
for the acids, you didn't do the plus H2O.
You know what? I probably should. I was just thinking about that. It doesn't change it too much because we're just adding liquid water, right? So the K expression doesn't change, but it would probably be more cohesive for me to include water. So we'll include water here.
So it's
H2O.
It's not in the calculation anyways. But
Correct. So
but
let me
if
change
they asked
this.
you to write an equation like that, you would put water.
I don't know if you would have to, because technically what I wrote is correct, but if we're talking about dissociating in water, it's probably better to write out water explicitly there, so thank you for that. We'll have HA aqueous plus water yields, instead of just hydrogen positive, hydronium. H3O plus aqueous plus, and then of course A minus aqueous. Okay, so it does change our expression, just how it looks. It's still the same thing, where we have the hydronium ion concentration times the A minus concentration over the acid concentration. Okay? Good catch, man. So here, it's important to realize that the Ka and the Kb are specific to the acid or base dissociating in water. Okay? If we had HA plus H, if we had HA plus B, the Ka or the Kb would not alone be enough to tell us what the K for this equilibrium reaction would be. Okay? We would have to do something else in order to determine the K for whatever reaction happens here. Okay? So just keep that in mind, that the Ka is specific to the acid plus water yields hydronium in the conjugate base, and the Kb for the base, or for bases, is the base plus water yields the conjugate acid and hydroxide. Okay. All right.
It's a great day to be a hurricane. Today is Monday, October 25th, 2021. Please join me as we stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please throw away all hesitation and talk and silence your cell phones at this time. We appreciate everyone working together to wear masks at all times, covering your nose and mouth when breathing
So here, you can think of it that way, but I don't think you should ever write a strong acid as a product, because it will always be, a strong acid in solution will always be just its ions. Does that make sense? So you could react those together.
Thank you.
It
The
would always be
ASAP
ions.
will be administered October 29th,
Yeah, it would
first
just be
report
all
period.
ions.
Sign up
It
with
would be
your
acidic,
guidance
but it would
counselor
be
or
all
at the NJROTC classroom. Boys basketball tryouts are Monday, November 1st. All students interested must have their EL2 and EL3 forms filled out and turned in to Coach Barnes prior to trying out. If you need paperwork, please swing by Coach Barnes' room. If you will still be playing another sport during the November 1st tryout and would like to try out at a later date, please swing by Coach Barnes' room and let him know that you intend to try out. Student League Sign Language Study Group every Tuesday at 7:30 a.m. in B5. Our Hurricane Players presents High School Musical Junior on Friday, October 29th at 7 p.m. or Saturday, October 30th at 12 p.m. or 4 p.m. Tickets are $10 for a limited time. Come out and support our fellow classmates. Box to the top and we'll see you there. Tickets can now be purchased online through the GHS web store. The last day to pay dues for the Asian Heritage Club is Friday, October 29th. After that point, only paid members will be able to attend meetings. Dues can be paid through the school store. The last workshop Wednesday is October 27th from 3 to 4 p.m. The topic is mock interviews. This is open to all GHS students. Registration ends tomorrow. Please see Ms. Becker for more information. All students are reminded to attend the final workshop from 3 to 4 in D2. Pizza will be provided. This Thursday, October 28th, BSU will be holding a meeting after school. Dr. Moss's classroom. All members must be in attendance. Check your email for more information. May Center a selfless act by joining us for a fundraiser to support Dance Marathon at Gainesville High School. Join us at Copper Monkey West in Jonesville Tuesday, October 26th between 5 and 9 p.m. Tell your cashier that you're supporting the Marathon at GHS to ensure 20% of your order will be donated to our miracle children. There is no Rikert Health pickup today. Please make additional arrangements for you to get home if you ride the Rikert Health bus. Also, as a reminder, Lady Kings basketball tryouts are today and tomorrow from 6 p.m. to 8 p.m. Monday and 6 p.m. to 8 p.m. Tuesday in the GHS gym. There is an informational meeting for boys wrestling Thursday, October 28th at 3 p.m. in the cafeteria. Psychology club photos will be held during lunch for 4th period. That note is not dated. That may be for last week. And that is all the announcements that I have for today. This is Mrs. Langenbach. Take the day by storm, GHS.
Okay. I wanted to make a quick note here that the hydrogen or hydronium ion concentration in this kind of example is equivalent to the A- concentration. Okay? So when you dissolve a weak acid in water, the hydronium ion concentration and the A- or the conjugate base concentration are going to be the same. Okay? You can see that in other examples when we set up our ice tables. It's both of those are going to be plus X and plus X. Okay? And then similarly for the Kb, the conjugate acid concentration is the same as the hydroxide ion concentration. So if you know one, you know the other. That's kind of what that means. Maddie?
Is that different from before when we oh wait, never mind, this is weak acids.
Yeah, this is weak acids, so they're at equilibrium, and so the acid concentration and the hydronium the hydronium concentration kind of depends on the Ka. You wouldn't be able to really make this claim without knowing the Ka. Any questions on this? Yeah, Maddie?
Sorry, and then
No, this is
also
great.
For before you said that strong acids are not liquids, they're solids. What about bases?
Bases are typically solids that you have to dissolve in water. Yeah, because bases are usually metal hydroxides, and so that's an ionic solid. Yeah, good question. Now acids are usually hydrogen halides or hydrogen. They're usually covalent. Is basically what I'm trying to say. All right. we're going to quickly get to math here. I want to erase this, give an example on kind of the relationship between Ka and Kb, and then we have 2 examples and we're done. Okay? So, here we go. Stop me if you have questions. We're still in 3, so. Put that there. There's nothing, I guess, new that we've learned so far, except for the fact on, these are acids and bases that we're dealing with now. All the ways that you calculate acid-base problems are the same. We've just kind of added a little bit of stuff to how we can calculate those things with the pH and the hydrogen ion concentration. Okay, so there's a relationship. Here's a little note. pKa plus pKb equals pKw. Okay. Now the pKw actually is 14. You can calculate it, but the pKw is 14. Okay. So pKa plus pKb equals pKw, and this is only true at 25 degrees Celsius. Okay. And this is also only true for a conjugate acid or base pair. Okay? You can't just take any old acids Ka and any old bases Kb and do the pKa plus the pKb and have it equal 14. That's not how it works. It has to be a conjugate acid-base pair. Here's an example. Hydrofluoric acid is a weak acid. So if we have it aqueous added to water, we get an equilibrium reaction where we have H3O plus aqueous and F minus aqueous. Okay, and this Ka is 6.8 times 10 to the negative 4. Okay. The acid in this example is HF, and the conjugate base is F minus. Okay, so we've identified an acid-base, a conjugate acid-base pair, where our acid is HF, so we have the Ka value. All we need to know now is the Kb for F minus. Okay, so here we would want to basically take, okay, what is the Kb value for F minus reacting with water to form hydrofluoric acid and hydroxide. Okay, so we're taking the Kb thing here. So F minus aqueous plus H2O is in equilibrium, this is a liquid, with hydrofluoric acid now plus OH minus. Okay? Do we see how this is the Kb, where we have a base plus water yields some conjugate acid and hydroxide? Basically, it's not the reverse reaction of this, but it's the conjugate base of this reaction reacting with water. Okay, so this is a base reaction, so the Kb here is going to be 1.5 times 10 to the negative 11. Okay, it's not a very high K value, so this is definitely a product favored reaction. Okay, so if we wanted to see how this relationship works, we would find the pKa and the pKb and then add them together to see if they equal 14. All right, so let's do that real quick. The pKa of hydrofluoric acid is basically the negative log base 10 of the Ka, which is 6.8 times 10 to the negative 4. And so what does this equal? 3.17, very good. Okay, and then the pKb of fluoride equals the negative log base 10 of the Kb, which is 1.5 times 10 to the negative 11. What does that equal? 10.82. Very good. So add those two together, and what do you get? 13.99, which is basically 14. Okay. So which 14, by the way, is the pKw, right? So this is true for acid, conjugate acid-base pairs, okay? This right here is the base, just to be complete, and this is the conjugate acid. Okay. Let's skip that, I already talked about it. So here's an example problem. Are we good on this? Makes sense? This can be helpful if we need to actually find the Kb. If we're given Ka, we can find the Kb relatively easily of the conjugate base. Okay, so that's why that's important there. All right, example problem. All right. Calculate the pH of a solution containing 0.100 moles, decimeters to the negative third, of nitrous acid, HNO2, of which the pKa is 3.33. Okay. That's actually enough information to find the pH. So let's work through this one. I'm going to give you guys a little bit of time to see if you can get started on it and figure it out, okay? I'll get you started a little bit. Just off to the side here, pH equals the negative log base 10 of the hydrogen ion concentration. Okay, so you're trying to find the hydrogen ion concentration at equilibrium for this system, then you can find the pH. Okay? So give that a shot and see what happens. I need water. I also need to take attendance. Definitely want to use an ice table for this question. At least that's how I'm going to solve it. So try to find a reaction that might exhibit what this solution is doing. Also, I forgot to mention this, but I did add 2 points to everybody's score on the quiz because there's a question that nobody got right, and I felt like I didn't prepare you guys enough for it. That would have been part A on the free response for AP. So that's completely aside. This is the starting concentration. Yeah, the 0.1 moles is the beginning concentration. Typically, unless it's explicitly stated, you don't want to say that the given molarity or concentration are at equilibrium. That's usually the starting condition, so initial. And then unless they say, oh, and the equilibrium concentration of whatever is that, then make sure that that's initial. Very good. I'm seeing lots of good work, you guys. I'm going to start solving this, how I would approach this. There's other ways that you can do this. There's ways that kind of speed it up. There's ways that are a little bit slower. But this is the way that I would solve this equation if we're approaching it from an equilibrium question standpoint. Okay? So we would first realize that this is a weak acid, not a strong acid. So this is an equilibrium question indeed. And so let's write out if we're given the pKa, the equation for Ka is the acid, so HNO2, aqueous, plus water as a liquid, is in equilibrium with H3O plus, aqueous, which is the same as H plus, right? So if we find the concentration of hydronium, then we're fine. So H3O plus our conjugate base, which is NO2 minus. Okay? And then I'm going to set up an ice table. We have I for initial, change, and then equilibrium. Our initial, again for water, since water is a liquid, we're going to just kind of do that because we don't care about water, because everything else is aqueous. So the initial concentration of nitrous acid is 0.100. Okay? And we don't have this yet because equilibrium hasn't been established. So we have 0 products over there. Since we only have reactants and no products, our reactants will decrease concentration. So minus X plus X plus X. Okay? And then our final concentrations will be 0.100 minus X, X, and X. Now, setting this up, we're kind of noticing maybe that, oh dear, we're going to have 2 x's up top and 1 x on the bottom. It's going to be x squared over something minus x. Oh my word, your heart starts racing. You're going to have to use the quadratic equation. But remember that little trick I told you guys about? If the initial concentration divided by the K for that reaction is bigger than 400, then you don't have to worry about this minus x. So let's actually find the K for this reaction. So Ka equals 10 to the negative 3.33. Okay? Because that's how you undo the P. So Ka 10 to the negative 3.33, this is 4.68 times 10 to the negative 4. And then if we're going to use our approximation, we have to check it first. So 0.100 divided by 4.68 times 10 to the negative 4. Did I even do that here? What does this equal? Can somebody do this for me? I don't know. I know it's bigger than 400, but...
213.
Sorry? 213?
213.68.
That's awkward. Well, let's ignore it anyways. It doesn't actually matter too much. If you did the quadratic equation, your number would be a little bit more on point. I'm going to ignore it because this is a low Ka. And because I don't want to do the quadratic equation. So the Ka, which we have here, 4.68 times 10 to the negative 4 equals x times x divided by 0.100. Okay? And so we can solve for x pretty simply by multiplying both sides by 0.1 and then taking the square root. So I solved x to be 0.006839 moles times decimeter to the negative third. Since x is the concentration of both hydronium and nitrite, okay, we've basically found what we're looking for. So just take the pH is the negative log base 10 of that. So 0.006839, and I got about 2.16. Did you guys solve this with the quadratic equation? No? Abigail? The trick is if you take the initial concentration divided by the K value, and if it's like, my number was bigger than 400, like that's when it's safe to use. This number seems a little too small for me to actually effectively use it here. Yeah, it's a little too small, but it was a bad example. I should have chosen something that was bigger than 400. Jake? Yeah, you could have done it a different way. It would have been fine. You don't have to do this this way. There's more than one way to do it.
Is the ice table always consistent though?
Ice table is always consistent. Yep. If it's not a 1 to 1 to 1 to 1 ratio, you might want to just check it with an ice table, because otherwise it's not just going to be x squared on top. Yeah, check it.
Did you get 4.68 over equals 2x?
So to calculate the Ka, I just took 10 to the negative 3.33. That's how you undo the P
okay,
portion.
never mind.
Yeah, so that's how you calculate the Ka. That's the Ka here, and then you just plug it into your thing. Yeah, in my notes, I just completely abandoned the 1.00. Maybe I was thinking that was the equilibrium concentration. So this is a very basic, like straightforward example, okay? There's lots of more complicated ones. I have those in additional problems. I have that in the worksheet, okay? So we're gonna have to work on those. The last thing I want to talk about are polyprotic acids and bases. You guys know what a polyprotic acid is? Yeah, Jacob?
Maybe like the anion has a charge greater or like different than negative one, so there's more than one hydrogen.
Yep, that's exactly what it is. There's more than one hydrogen that can be donated as like maybe in an acid, which means there's more than one Ka value and there's more than one Kb value for its conjugate bases. Similar concept though. Very good. So polyprotic. Okay. So some acids have more than one ionizable hydrogen. One example would be sulfuric acid, but I'm going to do sulfurous acid. Sorry. H2SO3 is ionizable, and so again, sorry, let me write the actual acid dissociation reaction, as in this is aqueous, and we are reacting it with water. It is in equilibrium with HSO3 minus aqueous plus H3O. Wow. My handwriting today is a little off. This right here is the first proton, basically, that can dissociate. And it has a specific Ka value. We denote it Ka sub 1, okay? And this actually has a value of 1.7 times 10 to the negative 2, Okay, so this is a pretty strong acid. That Ka value is pretty large compared to other K values, and so that is going to be a pretty strong acid. Okay. Now, we can actually take this conjugate base, and it still could act as an acid, right? If we reacted it with water, we would have HSO3 negative aqueous plus water in equilibrium with SO3 2 minus and H3O plus. Okay. Now this is denoted Ka sub 2. Okay, because it's the second proton that can be ionized as an acid. All right. Do we see how I'm seeing some confused faces? We have H2SO3 donating a single proton to make this, right? This still can donate a proton to water, and it can make this. Now, the Ka2 for this reaction is much, much smaller. It's 6.4 times 10 to the negative 8. Okay, so it is way smaller than the first Ka value. And that's actually true for every single polyprotic acid. As you continually remove a hydrogen, the next hydrogen becomes much, much more difficult to remove. And that's because when you remove a hydrogen, it's just a proton. It's a positively charged particle. And after you ionize it once, it's on a negative thing. So it's going to be harder to pull away a positive charge from a negative ion. That's essentially the idea of it. Okay? So the first Ka value is always going to be much larger than the second one, which is always going to be much larger than the third one. Okay? So we can actually do a calculation with this. So this will hopefully be pretty straightforward. What is the pH of a 0.0037 molar H2CO3 carbonic acid solution? Okay. And then as a follow-up question I have, what is the carbonate concentration? Okay. And then the Ka1 for carbonic acid is 4.3 times 10 to the negative 7, and the Ka2 is 5.6 times 10 to the negative 11. Okay. So approaching these can seem a little bit daunting at first, because for carbonic acid, we have two ionizable hydrogens, right? We can ionize the first one, which will form H3O+, and then we can ionize the second one, which will also form H3O+. So do we have to do two ice tables and then add those two hydronium ion concentrations together? You could, but you don't have to do that. And the only reason why is because the A2, the Ka2, is so incredibly small that the added hydronium ion concentration from the second ionized hydrogen is negligible compared to the concentration that you'll get of hydronium initially for that first hydrogen. Okay? So don't get thrown off here. I get thrown off by these a lot. Okay, I want to let you guys know you don't have to set up multiple ice tables here. Just use the Ka1 because the Ka2 is so much smaller than the first Ka. Maddie?
Will it always be like that?
It will always be like that. Okay? The Ka2 is always going to be way more smaller than the first Ka because it's just that much more difficult to remove another hydrogen. Owen?
Is there ever a situation where that would where we will have to do two ice tables?
There might be other situations where you have to do two ice tables, but not a polyprotic acid example like this one. Yes. Alex?
Is it acid like H3PO4?
H3PO4 will have three Kas.
Ka1 and K here.
No, still Ka1. Yep. As those continue to ionize, it just is less and less and less. It becomes super difficult to ionize those other ones. Okay? So I'm actually going to solve this one with you guys. So since we're only using the first Ka value, we're only going to be using that first equation. So we have H2CO3 aqueous plus water. Okay, it's in equilibrium with H3O positive plus bicarbonate, which is HCO3 minus aqueous. This is our reaction for Ka1, okay? Where we just take one hydrogen and react it with water. Then we can set up our ice table. So we have ICE. Our initial concentration for carbonic acid is 0.0037. Again, we don't care about water because it's a liquid. And our initial concentrations for hydronium and bicarbonate are 0. Then we do yield faithful minus X plus X plus X. And we get our favorite little thing here. We have 0.0037 minus X, oh dear. And then we get X right here and X right here. So at this point, this is where I tried my little trick. All right, let's take the initial concentration, 0.0037, and divide it by the Ka value, 4.3 times 10 to the negative 7. What do we get? It's above 400, and that's all we care about. This is above 400, and so we're good. We don't actually have to care about then this minus X, because essentially what we're doing is we're saying this minus X right here is so small compared to the initial concentration that even if we account for it, it won't change this value. Okay? So what we're doing is we're completely getting rid of it, and it makes our algebra way, way easier. Okay? So now we can go over here and just plug in our things to a Ka expression. Okay? So we have the Ka value, which is 4.3 times 10 to the negative 7, equals, okay, our products, the concentration of our products over the concentration of our reactants. So this is X squared over 0.0037. Okay. Solve for X. Which equals about 4.0 times 10 to the negative 5. Or that negative is and that would be the hydronium ion concentration. Negative log base 10 of that will give us the pH, which is what we're looking for. Which I found to be about 4.40. Okay. And then what is the concentration of our hydrogen carbon? Oh, yes, of our carbonate ion. This follow-up question means that we have to do the second Ka2, because carbonate is not in this equation. Okay, and so we would basically. Do you guys want me to do this? Okay. First off, any questions on how to calculate the pH over there? Just an application of equilibrium problems. You're basically just taking the negative log of one of the concentrations. So we have this concentration. This is the equilibrium concentration of hydronium and of hydrogen carbonate, right? So we can actually take our second equation, which is HCO3 minus plus water, is in equilibrium with CO3 2 minus plus H3O plus. Right? This is the second equation that we get from the second ionizable hydrogen. HCO3 negative plus water yields carbonate plus hydronium. And so we can set up another ice table here. Okay. We know that these are going to be 0 at initial. The initial concentration of this is what? What is the initial concentration of hydrogen or bicarbonate?
4.0 times 10 to the negative 5.
Very good. 4.0 times 10 to the negative 5. It's the final equilibrium concentration of this reaction. Okay? So we're just kind of taking what we started with, what did we get, and then we're taking what we got, that's what we started with for the next reaction, then we're going to see what we get after that. Okay? So this is, again, minus x, and we get x here. And then right here, let's just do our trick thing. Is this going to work? 4.0 times 10 to the negative 5 divided by 5.6 times 10 to the negative 11. Is this bigger than 400? Yes. Much bigger. So we actually don't care about this x. And so our final equilibrium concentration is 4.0 times 10 to the negative 5. Okay? At this point, it's, again, just the same thing that we did over there. So now we use the Ka2, so 5.6 times 10 to the negative 11 equals x squared over 4.0 times 10 to the negative 5. What is the value of our concentration for carbonate? Oh, so sorry. I went a little bit too fast here. My apologies. We actually do have an initial concentration for hydronium, right? We have a hydronium right here in our first reaction. So we do have an initial concentration for hydronium, which is also 4.0 times 10 to the negative 5. We're still doing plus x though. But the difference here is that because this is bigger than 400, we can also ignore that x. Okay? Sorry for that mistake. Do you guys see why we have to include that product there? Shadia?
Why is it the initial and the equilibrium?
It's the initial and equilibrium because we're essentially saying that the Ka for this is so small that even if we included it, we wouldn't be able to recognize the change.
Oh, okay.
Yeah. So this number right here is too big for this x to change, basically.
Okay, thank you.
And so since these two are the same, they're the same here, right? They're both x here, and we calculated x, all right? We have to carry that over into our next equation, okay? And so our this actually means that our equation is easier now. So we have 5.6 times 10 to the negative 11 equals this, 4.0, times 10 to the negative 5 times x over 4.0 times 10 to the negative 5. These cancel, and you get x equals the Ka2. And concentration, of course. Sean, did you have a question?
No, I got it.
Oh, okay. So that's just kind of a nifty extending that we can do for equilibrium concentrations there. Something that I need to remember clearly is that if we have a second reaction in our system, we have to remember everything that's present. In this case, both bicarbonate and hydronium. Jacob? Okay. That is the, yeah, Colin?
4.0 times 10 to the negative 5 of hydronium is not a product of that reaction.
Right. No, it would not be in the reactants because this K value right here is describing this acid right here, HCO3. It's describing this acid reacting specifically with water. Just because we have it initially in our system does not mean that it is a reactant. Okay? We can have initial concentrations of products and both reactants. That might change how this goes, but since we have 0 products over here for this specific product, equilibrium will still fit this way. It is possible to have initial concentrations of both products and reactants at the same time. So just make sure you're staying true to the K expression or this acid dissociation reaction, and you should be fine. Any other questions? Okay. This is it for lecture 3.3. Lecture 3.4 is going to be choosing an indicator for titration specifically, and then also solubility equilibria, which is, again, just another application of equilibrium constants, okay? So it's a specific kind of equilibrium reaction. I do have a worksheet for you guys, which I can have here. I don't know where I had it, so this doesn't make any sense.